In chapter 4 we said, let's say there's a spring and we compress the spring and then release it. The spring goes back to its own position. And we said we were modeling nature. We were saying, well, the object is stationary and suddenly starts moving, therefore there's going to need to be an acceleration. Because there's a change in velocity, there's an acceleration. Because there's an acceleration, there is a force. And that force, what is that force? And we call that the elastic force, or Hooke's law, which is restorative force. It goes opposite to the displacement, right? With a constant of proportionality, which is the stiffness or the spring constant. Very good. And that was Hooke's law, and that's what we described. So what we're going to see now is what is the behavior of solids under deformation, or in fact what happens when you deform a solid. And of course, to deform a solid, you're going to have to be making a force. And that force, which the way it works is that the force deforms the shape, and because it deforms the shape, the atoms inside try to recover the position. Why so? This is an important point to consider. Now, before we go for that, let's remember another thing that we discussed. If we plot the displacement, and here we see the elastic restorative force, we said that at first this goes, linear, with the slope being obviously k, right? And here we're taking the modulus, not to take care of the sign. We're not interested in that. But if I keep increasing and I put, let's say, 1 millimeter, 10 millimeters, 50 millimeters, at some point I put too much, and so the spring, instead of recovering, it just deforms permanently. That's the idea of what we say the plastic regime, where the deformation is permanent. This is the elastic. In the elastic, I deform, I release, it goes back. In plastic, I deform, I release, it doesn't go back. So that plastic is a permanent deformation. And finally, if I keep going like crazy, at some point I'm just going to break the spring. And so that's going to be what we call the inelastic regime. So we can also say that this is failure, right? At this point, the material fails, it breaks apart. So these are the things that we already observed and we studied in chapter 4 to introduce the concept of elastic restorative force or restorative force. And we said every solid in approximation behaves in an elastic manner. And that's actually true, and we're going to see why in a moment. So important thing to bear in mind in here, this elastic force is a force that the atoms do. And because you have the object and the atoms are trying to push, if you something in contact, that's pushing, so that's pushing you, right? That's why we were using, for instance, a ball, you compress the spring and it goes back. Okay, that's also a structural thing, but anyways. So let's take an idea here and let's see why this happens. Let's say I have a block, simple object, and I analyze, it's just free, right? So it's free, and I just let it go. What happens at a certain height? Well, I do free body diagram, and I observe that the object has certain weight, and so when I do the balance of forces, the only thing I'm going to find is the weight equals mass times acceleration in y. The weight, of course, is mg, so that's going to be minus mg is equal to my. So that, of course, means that the acceleration or the object is going to accelerate with negative g, g being, of course, the gravitational acceleration. This is trivial. I have an object, I let it go, the object falls. Why? Because there is no balance of force. Let's analyze another scenario. Let's say now that I take the object at the same height, if you wish, right? At the same height h, and now I'm going to put it on top of a shelf or a table or something like that. It's at the same height. And then I ask, what happens now? It does not move. So why doesn't it move? So if I analyze the velocity now is 0, I wait, later velocity is 0, so the change in velocity is 0, and so the acceleration is 0, exactly. So acceleration is 0, there is no motion. Now there's no motion. I say, why? This object is falling, but here's not. And then we said, okay, if there is an acceleration, there needs to be a net force. If there is no acceleration, there is no net force. And so we posited there's something which is keeping the object in there. And of course, if we make the free body diagram of that table, we're going to still have the weight, but now we have a force, which is the normal force that's pushing up. And when I make the balance of forces, now what I'm going to find is I have the normal minus the weight, and that's mass times acceleration in y. But we said this is 0, so of course that means that the normal is equal to the weight. And we say this object is in equilibrium, right? So that's why it doesn't move. Why I'm bringing this up now? Well, that's going to be to understand why there is restorative force in the solids. Again, when we have a net force, there's an acceleration. To have an acceleration, you have to have a misbalance. If the net force is 0, if net force is 0, then there is what we call equilibrium. And we'll see this more explicitly in a second to analyze stability and all that, but for the time being, that's what we're going to say. And now we go back and observe something that we observe, for instance, physically. Let's say I have a rubber ball or whatever, right? There's a rubber ball, and then suddenly I apply a force. Let's say even like a compression force, right? Let's say I'm just pushing it down, it's on the ground. What do I observe? Maybe what I observe is that that thing goes like this. Okay, I still applying the force. And then I release the force, and what do I observe? Well, what I observe is that the ball just goes back to the original thing, right? So I apply a force, or let's just do it in here. No force, the object is like that, perfect, round. I apply a force, the forms, the object release the force, the object goes back. So now I need to understand this thing. Why does it go from the form to not the form? And that's going to be answered by the same principle in here. Once I have it the form, what I'm having is, I'm going to have, if I go to the atomic level, what I'm going to see is that the atoms in here are all arranged nicely, and they're interacting with each other. And the balance of forces, for instance, of this atom is going to be the force of that atom neighbor, let's call it 1, 2, and I'm going to say, oh, this is the force of 1 on this one. I take this, let's take this atom in here and say, oh, what forces this atom is experiencing? Well, it's experiencing a force of, let's say, repulsive force of atom 2 on him, and it's also experiencing a force of atom 1 on him, right? So why doesn't it move? Because the forces cancel each other, so they're the same force. So the interaction force between atoms are indistinguishable, and they're applying the same force, and so forces cancel, so the atom is in net zero force. It doesn't move anywhere. But as soon as I apply the formation, then what I'm doing is adding an extra force, and as a result of that force, maybe, yeah, I will still have from my atom, and now I have a new force. Let's say if I go perpendicular, we could go sideways, that's fine, right? I have the same forces before, this cancel, but this one now is net, so there's a motion. How much? There's a motion to the point where the atoms from the bottom, let's say, start to push back and start to balance that force with, let's say, atoms, let's say, if this was the solid, right? Let's say these atoms like this. I'm analyzing this atom, but there's also a second layer of atoms in here, right? So now I'm going to be pushing this atom down, and this atom is getting close. As it gets close, the force of repulsion of this one is going to be increasing. You will see that because that's electrostatic force. It increases with the square of inverse of the square of the distance. So now it's increasing, and so I'm starting to find a restorative force that, and this is me pushing, right? I have a restorative push, and wherever that thing balances, the thing stops yielding, right? Yielding, and then what I have is an equilibrium. Well, once I release it, because these atoms are now they're like this, right? This atom is going to be pushing that guy back. But once I release the force, this goes out, and so my next situation is going to be like this. The force lateral, let's say, but I'm going to have a restorative force, but I don't have push anymore. So now I'm going to have a net force pushing upwards. So the object goes back to the position wherever the atoms, which will be like, this is the intermediate state, and then the thing would go back to the situation where the atoms are all arranged, and are all arranged in the same, supposedly in the same scenario now. And now again, I recover a scenario where all the forces are balancing each other. So this is why solids recover themselves. But this is the important thing. Of course, if you go too crazy, at some point you can break it, or you can make a deformation that remains forever that way. And so that's going to be the plastic regime. And if you go like really crazy, you can actually break the atoms, right? So this breaks, you have two solids. That will be like an elastic thing. If you go, for instance, if I start stretching, it tries to recover, but at some point, it's too much. It just goes away. It breaks, right? So this is from the microscopic perspective. What's happening in here? What is determining this behavior? And the idea now is going to be, how do we mathematically describe this? One thing to notice, however, we're going to limit ourselves always to the elastic regime. Why? Because in this regime, which always is true for sufficiently small deformations, then the mathematics becomes a little more simpler. This is what engineers do for a living, so at some point it becomes too mathematical, and I am not interested. But I'm more interested in the concept. So we're going to be always behaving in elastic regime. We're going to analyze how mathematically we can describe the solid's behavior. Now, just one thing here, again, just to complete the picture, but it's not going to be that relevant anyways, it's just to understand exactly how it works. What happens when I have my solids in here? I have the things, I have the form, and I'm observing this from the point of view of potential elastic. What is the potential elastic here? 0. This is what I define as my reference, right? Let's remove, let's say, the breaking in this example. This is what I call 0 potential elastic. 0, this is my 0. What is the situation here? Remember, potential is depending on the force. Why the force is elastic is a potential force? Because it depends, on the position. Because once I have deformed the positions, I have changed the balance of forces. And so the thing has stored internally, remember potential energy is stored, so I have stored internally the capacity of using that net force then to put something else in motion, in this case the atom itself. And so when I deform something, now I understand I'm putting energy, I'm storing, I'm going to my bank and depositing in the ATM some cash. I had motion here, I put it in there, but whenever I remove that thing, if their balance is broken, I can extract that motion. And that's also the idea of potential elastic energy, right, is going to be non-zero. Now I understand that I need to put some work to deform the structure. Once I deform the structure somehow stores that energy, and that energy is going to be available then to be used later on. This is just for the sake of completeness anyway. But the important thing from this chapter, let's analyze how we study deformations in solids, and in particular in solids within the regime, within the elastic regime. There will be some problems when we analyze an elastic, but for that point of view, the same elastic regime, let's keep it there, and then we will ignore the plastic and go directly to the inelastic to say, hey, will this be enough or will the string break? We saw that those ideas anyways before, but we just see them more precisely now. So to describe deformations in solids, right, deformations in solids, which is basically the idea of this chapter together with stability, we'll see next. We're going to have to introduce two terms or two things that are important. One is going to be stress, the other one is strain. Before we go to that, of course, let's see that we start saying, I have an object, a solid object, I apply a force, the object deforms, so I apply force, let's say, I apply a force, the object deforms, and because the object deforms, the object has a restorative force. That restorative force, so we can call the stress. Because I apply a force, the object deforms. Because the object is deformed, then the atoms have a misbalance of forces, they just try to recover. That's what we call stress. So stress is actually the filling, so to speak, right? If you want, we can call it the filling of the atoms. And we can, again, the stress is a word that we use a lot in our common day-to-day, which of course draws back from the same idea. Why do we say we're stressed, for instance, in an exam? Because there's a force acting upon us, and it's just deforming us mentally, right? That's the load. There's a load into us. What's the load? It's like there's an exam coming, I'm stressed. Why? Because there's a lot of pressure in there, half the pressure, so I stress. But stress is mine, it's not the environment. The environment that might apply a force, and as a result of that, eventually I develop stress. So it's important to understand that stress is the reaction of the material of that, right? So, but this is the material doing its own thing. So it's the result, of course, of something external, but it happens in the material, okay? So this is the first distinction. And the thing we're going to analyze in here is stress. We're going to call it sigma, okay? S, sigma, right, the Greek S, okay? And we're going to say, when will I feel more stress? When will I feel more a reaction to that thing I'm experiencing? Whenever someone pushes slightly or when someone is pushing greatly or largely. Of course, I'm going to feel more stress the more load there is, right? So sometimes whenever you have an engineering, they use the word load whenever something is under a force, right? So for instance, I put my hand and I start putting things, I start loading things, so I feel the weight, right? So that's the idea. So the larger the force, of course, the larger the stress. So stress is going to be linearly proportional to that. But there's also another thing that we can realize is that for the same experiment, let's take again and say I'm pushing down on a solid made out of atoms, right? And then say, okay, I'm going to compare the case where I'm pushing with, let's say I'm putting, let's put some more atoms here. And let's compare the case where I am pushing like this, right? This may be my finger, whereas I'm pushing with the comparison with the situation where I'm pushing, for instance, with a needle. Maybe let's put the needle here. That's supposed to be a needle, okay? And I'm saying, okay, which one produces larger stress? Now, when I have my finger, the area in contact is larger. That means the more atoms I am affecting. So again, the amount of force I am distributing is the idea of the nails. It goes there. So the stress here is going to be lower than, in fact, where the needle, which is why the needle pierces through. It just reduces the area, right? It would be horrible if they were trying to push you with a big needle, right? Because you have to make a lot of force. So that's what we use, sharp needles and so forth. But anyway, so here we're distributing the entire force into the area. The larger the area, the smaller the stress, because the atoms are going to, less of the atoms are actually going to be, excuse me, the atoms are going to feel less of the force because the force is being distributed between the different atoms. Whereas in here, in the case of a needle, that's supposed again to be a needle, right? So the area of contact is smaller. If you want to think in terms of microscopically, there's less atoms receiving that force. So the smaller this, the larger the stress. That's not difficult to see. We see that, we understand it. That's in terms of stress. This is the first component that we need to define. There's a second component that we're going to define, which is called strain. Very good. And strain is going to be called epsilon. And we define a strain as the relative change of an object's length to its original length in the direction of the force, right? So let's say that there's a pipe, and we will analyze this in a second more profoundly, but let's say I push down, and this is the original length, right? This is, original length, right? That's length. And then after I apply a force, the object compresses, and now it's this big, right? And it goes this length. So then I calculate the change in length as the final length minus initial length. And that's going to be defined in the strain. Of course, if I compress, final length is smaller than the initial. That's negative. Negative, this is always positive. This is negative. Strains will be negative. If I stretch, the final length is going to be larger than the initial. That's going to be positive. Strain is going to be positive. But at the end of the day, strain is just telling me the ratio of, the ratio of the change in length to the original length. And now there's one last thing that we can observe in here. When I apply a force, things are going to stress. How much they stress are proportional to how much they deform. The proportionality between the stress and the strain is given by what we can say the elasticity. And we're going to observe and we're going to try to find out exactly what is this elasticity. But before we do so, let's realize one thing. Stress is the force over the area. But there are two scenarios that we can observe. Force is a vector, and it has direction and magnitude. In our case, we always have been treating 2 dimensions, but this could be more dimensions. So in general, stress is going to be, actually strain is going to be a tensor, but that's well beyond the scope of this class. But let's say a force, and I can take, there is an object, for instance, let's say there is a block of, let's say a block of gelatin, okay? And we can use that for the rest, okay? And then let's say, okay, I can apply a force like this, and this is sitting on the table, right? And this is going to compress. That will be a force which is what? It's normal to this area, which is where the one that I'm applying the force. So that normal force right? I'm going to find that's normal force is producing a normal stress. But there's also the possibility where the force is not acting like this, the force is acting parallel to that layer. So let's say I have this and I just push like this. I don't push down, I push sideways. And that's a parallel force, we can call it F, and then the 2 bars, again, that means parallel, right? The 2 bars is just a way of saying parallel, because if I use P, that would maybe be confusing with perpendicular, I don't know. So we say parallel. And that force doesn't really deform the object. Imagine this was gelatin, and imagine there is friction on the table. If there's no friction and I take the object and I just push, it just goes sideways, of course, because applying it in here is going to be the same as applying it in there, right, on the side. So it's going to be applying it here and applying it in the face is going to be equivalent. But when there is friction in here, this layer on the bottom, as I apply a force that tries to move the object in that direction, there's going to be a force of friction. And look what's happening here. I have a force of friction down here, and I have no force of friction in here. So this is going to be able to move, but this one is not going to be able to move. So what happens when you push gelatin like sideways? That the thing is going to deform. So it's just going to end up a block of gelatin like this, right? And that sort of stress is also going to deform the object, therefore there's going to be a strain, but now that sort of stress is going to be what we call shear stress. And that is responsible for shape. Whereas this, and we're going to call it sub S, whereas this one whereas the normal stress is responsible for, or is the result of size. So we can say the size deformation, which is going to be with a strain, normal strain, is going to produce a stress. But the shape deformation is also going to produce a stress. And we're going to distinguish between those two, normal stress and shear stress. And we're going to analyze those, and we're going to see it mathematically in a second. We're going to do first normal, and then shear, which is basically the same, but just making there a distinction. And more importantly, we're going to try to find out this elastic thing, and what are things depend on the elasticity of the material. So let's start analyzing the case of normal forces. Remember that any force is going to be a vector, so you can decompose into normal and parallel because those are orthogonal. So you could always decompose any force that an object experiences as one force, one component of the force is going to be responsible for the forming in size, the other one is going to be responsible for the forming in shape. If you go fully perpendicular, there's no force that's forming in shape, there's just purely the formation in size, if you wish. Whereas if you go fully parallel, you're not going to deform in size, you're only going to deform in shape. Anything else in between is going to be decomposed into the two, with a proportion, a component being responsible for shape and a component being responsible for a size. But we'll not make it that complicated anyways. The first thing we're going to see is trying to analyze the elasticity, but the inelasticity from the point of view of shape, size elasticity, let's say. Size elasticity. So this is the first thing that we want to analyze in this case. And what is this? Let's take a block of gel. Let's make it like this so it becomes more obvious, let's say. Okay, right? And now I'm applying a force. Now the entire force goes perpendicular. And again, let's make it just explicitly, but this is what I just said. If I am applying a force that goes, this is my object and the force is applied diagonally, right? I can always take this force and say, oh, there is a component here which is parallel, and there's a component here which is perpendicular. And so depending on the angle in which I'm applying that force, then I'm going to use SOHCAHTOA to say how much is, the normal force component, how much is the parallel, and I split it into two and say this is much as shear, this is going to be responsible for shear, which is the formation in shape, this is going to be responsible for normal stress, which is sigma n, and it's going to be responsible for size change. Okay, this is shape, this is shape. So that perpendicular force is going to deform the shape, but also compress it, for instance, right? And the same thing we could do it with if we were pulling, right? But anyway, let's go here and let's assume we're just pushing down. As I'm pushing down, or after I'm pushing down, I've just observed that the object gets reduced in size, and it gets reduced in this direction, okay? So then I can calculate this as the L length, and this is going to be defined as the length original. And so now I have initial length and final length. Once I push down, I know that this object is going to be experiencing what we said in Hooke's law, it's an elastic restorative force. Let's just again be concerned about the magnitude so we don't have to write the minus sign. But we know that's proportional to the constant of stiffness or spring constant and the deformation, which in our case, that deformation is going to be delta L, right? So that's going to be K delta L. Now let's do some fancy things. Let's divide everything by area. So if I divide everything by area, then I'm going to have the force elastic divided by area. That's equal to K divided by area, right? Both sides divided by area times the delta length. Okay? What is this? That's a stress. Okay, that's a stress, and because this force is elastic, it's in the direction of the deformation, that's going to be actually the normal force. Okay, the force elastic in this case is in the direction of the normal force because it's perpendicular to this area where I'm applying the force. Okay, so that can become normal force. Then this is sigma n. Let's do something in here, over here. I can always multiply and divide by the same number, and then it's going to be the same. So I can always multiply times L0 and divide by L0, right? So I can do times L0 divided by L0 because L0 divided by L0 is 1. So that's going to give me Ka L0 delta L L0. But how much is this? This will be defined as a strain. So I can rewrite that as K L sub 0 area times normal stress. So let me rewrite that thing in here. So I have now the normal stress is K L sub 0 divided by area times strain. And now what I'm going to do is call all of this Y. Why? Because it comes from Young's modulus. Young's modulus, so we can rewrite the entire thing now as this simple equation. Whenever a force produces a strain, the strain times the constant of elasticity in this case now is going to be Young's modulus that ultimately goes back to how it recovers, is going to give it's going to produce this stress. Okay, so now we have a complete description. If I want to analyze how much an object deforms, a solid into the elastic and always into the elastic regime, I'm going to be using this equation. What's the stress, what is the strain, and what is the proportionality? The proportionality, the Young's modulus, is going to come from, excuse me, it's going to come from a handbook. Right, the handbooks are books that contains all the materials and different properties, so engineers use them all the time. So you don't have to use this one is going to be provided. But the rest one are calculations that you can make, or basically you can determine Young's modulus based on strain and stress as well, right? Now, one thing to mention in here is, because of the way I have derived this, which usually we should derive it the other way, but there's also historical considerations and all that thing. But one of the things we need to know is that Young's modulus, it does not depend on the shape or the geometry. This is purely a material property. Do you remember when we were talking about density and saying it doesn't matter, it's big or large, it is always the same. Still, density is always the same. We're going to find now that Young's modulus is always the same and only depends on the material. So still it's going to have Young's modulus, wood is going to have a Young's modulus, rubber is going to have a Young's modulus, and so forth. But each one of those is going to have the same Young's modulus regardless of the shape of the thing that you've made. Okay, and this is very important. Now, however, you can come back and let's erase this right now. We can come back and say, well, wait a second, because of this derivation we've made, I just end up saying that the Young's modulus was, that the Young's modulus is equal to K L sub 0 A. And I say, hey, but this is the length, this is the area, right? So Young's modulus actually depends on the shape. Not really. What happens is that the constant of a spring, the spring constant, is the one that actually depends on the length and the area, not the Young's modulus. So the way we derive it is because I wanted to draw from the things that we introduced before. But in reality, we should go from here to Hooke's law, not the other way around. And so if we do that, we can solve for K, and then K, we're going to see that it is Young's modulus, A divided by length. And this makes sense. When it's more stiff, a spring, whenever it's larger or when it's smaller, whenever it's longer or when it's shorter. So the shorter it is, the more difficult it is to stretch it. The larger it is, the more difficult it's going to be, the stronger the spring constant, right? And this is just the material. So here we have that this component is the geometry, and this one is going to be the material. So those both considered actually are the ones that define the spring of the constant spring, right? But the Young's modulus, it does not. So although we've said this, you can probably forget it. Take this as a given. This comes from experimental characterizations. Young's modulus depends only on the material. It does not depend on the geometry. I'm going to say it again. It does not depend on the geometry. This depends on the geometry and depends on the material. Depends on the material through Young's modulus and depends on the geometry through this. And again, this is some simplification, but anyways, Young's modulus does not depend on the material. Let's say one more time. Young's modulus does not depend on the shape. It just depends on the material. Every material has a Young's modulus. One extra note for Young's modulus before we close and go for shear. Again, Young's modulus is going to give us a measurement of the size elasticity, right? So it's the elasticity. Young's modulus is telling us how something is how elastic is something in terms of deforming its shape. Excuse me, its size, elasticity, the length, right? Another thing we want to say in here for Young's modulus is we're compressing the object. Well, if you stretch it, what if you apply a tension? Instead of being a compressive force, what if you do a tensile stress, right? So if you have an object and then you push it down, this we call compressive. But if you have an object and you pull it up, you also produce a strain, but this we call tensile, right? So both compressive and tensile stress in this model work the same way. The difference is that for compression, under compression, strain is negative because the final length is smaller than the initial. And under tension, the strain is positive because the final length is larger than the initial, right? This final length, and initial length, that's right. So that's the thing. So stresses in compression is going to be negative, stresses in tension are going to be positive. And nothing in here that we have discussed, the sign is going to come through here, nothing in here actually changes. So Young's modulus, as I said, it depends on the material, that's it. The truth is, however, that nature, of course, is a little bit more complicated and tricky, and some materials, although most of the materials, or in a first approximation, you can say most materials have the same compression and tensile Young's modulus. You can actually derive a Young's modulus for compression and Young's modulus for tension. And some materials actually depend whether you are putting tension and compression, and this is essential for structural engineers and architects, engineers and all those guys who are designing structures that need to that suffer loads. And that's not just simply building a building. Also an airplane, when it's landing, the wind or the pressure in the air on the wings, or a submarine or a boat or this and that, everything is going to have a pressure. And so you need to see exactly how the forces are acting and how much is the strain, and choose the material according to the Young's modulus, right? And you need to know, is this material under compression or tensile stress? And we will see that there's as we saw in the lectures anyways, there's this example of historical relevance, which is the development of the arc by the Romans. And it pays maybe just to see it, we will see it later. But just to leave the idea in here is, under compression and under tensile stress, typically Young's modulus is the same because it's just a material property. But because of the way some materials behave, actually behaving in compression or tensile is going to be, in tension, is going to be different for them, and Young's modulus is going to be different. Young's modulus is going to be provided to you in an example, unless the problem is actually to calculate the Young's modulus. This is experimentally demonstrated, obtained and calculated, and then people write the handbooks, and so you have a handbook of materials, or the manufacturer gives you Young's modulus, right? You find, oh, I want to buy this plastic thing, and the manufacturer gives you a spreadsheet with all the materials properties, and one of those is going to be the modulus of elasticity, or Young's modulus in short. So we have to find what happens when you go normal to the surface, but we need to now see what happens when you go parallel. So let's again imagine this is a gelatin layer, right? And so I'm pushing the top layer with a force, which is going to be a force parallel, and I'm going to be producing also stress. That stress what we call the shear stress, which is of course the parallel force divided by the area upon which this is acting, and this is the area it's acting. So I'm pushing that. I'm not pushing down, I'm actually just going sideways. If there is friction in this layer, I can see that this one is going to be remaining, but this one is going to move. How do I see that atomically? Also because the atoms are trying to keep together. So I'm going to be applying a force that tries to put this first layer in motion. So what happens when I'm applying that force is that I am displacing that, that layer. So I am displacing the layer, right? So this obviously exaggerated or whatever. So this one is going to be displaced from the original point. This one, however, is going to feel some force because this is pulling from this one through the interaction forces, but this one on the bottom is trying to pull those as well. So what's going to happen is that actually I'm going to see that this one displaces less, and finally you have the last one, which doesn't displace at all. And so you see what's happening in here? You had this, and now you have that. Because over here we're going to have a friction force that's acting opposite to the motion, and here I have a pull force. This is a cross section, of course, and this I have the pull force that I am applying in parallel. That's the parallel force, right, which is the parallel force. And because of that, this layer experiences the forces, tries to move. This one is being pulled by that one moving, but it's also pulling by this one to remain in position. And so I'm going to have a deformation of the shape. The volume here is the same, okay? There's no change in volume in here. And so then I can define the strain, but how I'm going to define here the strain for shear? I'm going to call it epsilon sub s, and if this is the original shape, let's say, and this is the new shape, what I'm going to calculate is the displacement with respect to the equilibrium position divided by the distance to the other layer where the object is receiving the force. Okay? So this distance, we can call that h or t or whatever you want to call it. Let's call it, for instance, h. Okay? And that's going to be what? The ratio of how much is moving from equilibrium divided by how far it's from that layer. And so that's going to be the definition of shear strain. This is the definition of shear pressure, and I can build my equation for shear stress, which is going to be elasticity times stress. What do we call the elasticity now? We're going to call this capital S. And that it is the equation, it's the equation that we're going to use to describe shape deformation, right? That's going to be shape deformation. So that's the idea in here. So that normal stress is producing size deformation. Shape deformation is going to be proportional to how much it strains, how much it changes the shape, proportional with elasticity. That's going to be shear elasticity. Again, that property is going to depend only on the material. some materials are going to be able to deform in shape better than others. So rubber is going to be easier to move than actually concrete, right? So the harder it is, the more difficult it's actually going to be for a given force to actually produce a strain, because the stress is very little or whatever, right? So you can play with these numbers, but anyway, this just completes the description of shear stress and normal stress, which is responsible normal stress for size, and shear stress is responsible for shape. So now we understand how it works, that whenever I apply a force into a solid, the solid can be compressed or stretched, it can change its size, but it can also change its shape. This is the mathematical description, which is what all we were trying to have, is a quantitative assessment of that and a microscopic definition. And again, we don't enter into this, it's just to understand the ideas, where they come from, because otherwise it's like I'm just making them up, right? So this makes sense. Examples of shear stress. Take a book, put it on the table, that's a classical one, push on the cover, you're going to see the book kind of deform sideways, right? Other example, but the volume that it occupies is the same, you can calculate that as well if you want. Other examples, what happens, for instance, or a limit of this, there's also a limit in elasticity. If you're in the elastic regime, it goes back. I release and the stress puts it back in place. If I have a gelatin or a jelly or whatever, and I'm pushing it on the plate, it moves the top layer, but if I release, it goes back, right? Why? Because we are in the elastic regime. In the elastic regime, whatever displacement is going to have elastic force enough to recover that, right? To put in motion so it moves back to the original position. At some point it goes plastic, and at some point it goes inelastic. What will be inelastic in here? We were saying it before, inelastic is when things break. So let's say I put a lot of stress. This is pulling, and one of those is going to break. So if I keep going this way, maybe I may end up in a situation like, let's write it here, right? When I keep going, at some point the atoms are too far away, and then this thing maybe breaks, and I don't know, maybe breaks like this, or who knows how. That actually depends on the structure, right? And I end up having two pieces. So shear stress also can destroy it. One, when you go into the inelastic regime for shear stress. It doesn't need to be only about size. Example of this, let's say you're in snow in a mountain, there's snow, and suddenly there's an avalanche. Why that happens is actually there's a break. Layers of snow slide with each other, they don't have any more retention, the interatomic or interlayer forces, the interfacial forces keeping the surfaces together, van der Waals forces or whatever, they're not enough anymore. The thing breaks, you go to an elastic regime, there is catastrophic failure. The same thing happens with mud in the mountains and things like that, right? So that's an example of shear force. It's not actually the compression or extraction, it's also trying to deform. So if I start pushing in here and pushing in here and pushing in here, and I go hard enough, at some point I may just break the marker, and that would be an example of shear. I'm not applying the force, let's say I'm perpendicular, I'm applying the force actually now lateral to this cross section, right? How exactly it breaks and all those things is well beyond the scope of this course. Let's just be aware that these things happen, but eventually this is what the engineers do for a living, and designing and structures and ideas and strategies, how to reduce those, or how to increase the maximum tensile stress or maximal compression stress, and also maximum shear stress, and so forth. The last part of this chapter on physics of solids is going to be related to what we call statics. So you remember in the introduction we said that there is 3 branches of mechanics. There's the first branch of mechanics that deals with how objects move, that we call kinematics. There's a branch that describes why objects move, or why they change their state of motion, to be more precise, which is dynamics. And then we said there's a third field of mechanics, which is why objects do not move. And that's what statics is about, because things are static. So we will analyze what makes things to stay stationary. And this is not trivial, because every object that is on Earth is going to be always experience at the very least one force. And that force is the force of weight, is the force of the mass, or due to the mass of object being massive and being an attractive force because of the planet, right? So in any scenario we have always at the very least weight force. And so if I calculate what is the net force for this scenario, I'm going to have a net force that is non-zero. And because I know that the net force, let's write it in here just to remind, this comes from Newton's law, it's equal to mass times acceleration. Every time I have a non-zero net force, I'm going to have an acceleration that's non-zero, which means I'm going to have a change in velocity. Final velocity is going to be different from initial velocity. So the object, if it's stationary, is going to start dropping, right? That's the idea that we see. Why do we see sometimes objects not moving? That's actually, that's funny, but we're used to see things not moving unless we push them, but in reality we should be asking, why are things not moving? Because they're always under, at the very least, the attraction of gravity, right? So how the tables, turntables, how the tables turn. So now we see, next example, we were discussing that before. We have, that was the office reference anyway. We have an object on the table, and at the very least it has a weight force. Why is not moving, well, it's not changing its velocity, it's stationary there, I wait, it's stationary there. So velocity is the same, it's not the same, okay? Why is the velocity changing? Why is there no, so we would go the other way, right? Final velocity is equal to the initial. There's no change in velocity. There's no change in velocity, that means there's no acceleration. If there's no acceleration, that means the net force needs to be equal to 0. So, why is the net force if it is 0? There needs to be another force. What's that other force? Well, that's actually the normal force of the table pushing on that object. And so then I understand that. The condition when force, the sum of all the forces, or the net force, it's 0, is what we call the equilibrium. And statics is about finding the equilibriums and seeing the conditions for equilibrium. This can become very complicated very quickly and very boring. I guess it's something passionate topic for engineers, but not for us. So, or at least not for me. So I'm not going to be interested in this, but at least the concepts we need to know. And we're going to simplify everything to try to offer very simple recipes to analyze equilibrium scenarios, right? There's many textbooks where they're going to develop a lot of time into this, and inclined planes and pulleys and this and that. I don't see how is that interesting for anyone doing physics 2053 for a first approach to physics. But again, from an engineer standpoint, I totally get it. Anyway, that's the statics again, why objects do not move, right? And we have an answer here, when objects do not move. Now, there's two types of motion we said, right? Motion can happen in translation, but it also can happen in rotation. And we said, what is the force in translation is Newton's law, right? So if we say we want to have a sum of forces in equilibrium, the sum of forces needs to be 0. So that's, let's say, the first condition of equilibrium, if you wish. To have equilibrium, which is no net force, there needs to be not force, and the object will not move, either vertically, horizontally, or in either direction, translationally. So if I want to have equilibrium translational, I need to have no net force. But that's also rotation. What is the equivalent of force in rotational motion? Well, that's torque. And what's the equivalent of inertia, or mass? That's I. And what's the equivalent to acceleration? Alpha. So then I see that if I want to have rotational equilibrium, I'm going to have the same thing we said for force, but for torque. And that is the second condition of equilibrium. For an object not to be moving, to be in equilibrium, I need to have no net force, but also no net torque. And this is trivial from here, but most of the examples we're going to be observing are about having no net torque. Why? If I take a pen like this marker and I leave it there, the marker doesn't move vertically and it does not rotate. But if I start pushing it, at some point the marker is going to start, if I go out of equilibrium, right, the marker will just, if I put it a little bit more, it just drops. So in reality, first it rotates. So what I can observe is that the marker is actually, so we can put it in here, so the marker is actually rotating with respect to what axis? Well, the axis is the last point of contact. So if I have the table and I put the pencil, right, I keep pushing the pencil, let's say this is the pencil or the marker or whatever, at some point, as I keep pushing, at some point the pencil is just going to start rotating. And this is going to be the axis of rotation. So what's happening in there is that I have no balance of torque. And why is that? Because as I'm pushing and pushing and pushing and pushing, at some point more mass is not being controlled by the normal force, let's say, and so the weight in here is going to be enough to actually, I'm going to have a net force basically. I'm going to have a net force acting down here. So if I push it enough, a net force acting in there and then tilting this thing. Why? Because that force is going to be tangential to the motion of the circle. And a tangential force times the distance to the axis of rotation is precisely what we call a torque. So then I see I'm going to have an unbalanced torque. Now, important thing to notice here, and we will see this in the problems, it becomes more easy, but just to understand the idea. Important thing is, of course, I'm going to have a torque here, and I need to have another one. But if I have another one, the other one is not going to be going up here. It needs to go down. If I want to stop the pencil from actually tripping, I need to push down. So I need to put the tangential force that acts on the other side of the axis in the opposite direction. So I have to have a negative torque. If this is positive torque, then there needs to be negative torque, right? So don't make the mistake of saying, no, I need to push here because I have the thing, and I push here, then I'm just advancing that. Now, what is the point at which, because if I go slowly, I observe that everything is fine, but at some point the entire thing falls. What is that point? Well, that point is the point of equilibrium is going to be with respect to the center of masses. And that's the condition of stability, is the second condition. Before we go that, let's analyze the idea of center of mass. So again, the idea of a center of mass is, let's say I have a pencil and it's just hanging there, right? And that's okay, but at some point I push it a little more and it starts rotating, so it just goes in a circle. And I'm saying, well, okay, the object was stationary before, but it's not stationary later. So we can repeat the same thing as for rotation. There is a change in the angular velocity. If there's a change in the angular velocity, that's the angular velocity is non-zero. That means there is an acceleration, angular acceleration, which is non-zero, which of course means that the torque is non-zero. So there's going to be a torque acting in here that actually puts in this thing into motion, right? And that's the idea. But how do we analyze this? You remember we did one of the first things that solids are extended, and then we need to analyze each one of the points. We saw in the case of translational, because translation always moves any 2 points into the motion, keep being in line. So let's say a motion in translation, if I take 2 points on this object moves, whatever it moves. At any point in time, I can see the 2 points, I can make a line, and I'm going to see that the line that these two objects describe, it's parallel to itself always. That's the definition of translational motion, okay? But anyway, so then with a single point, because the direction is always the same with respect to the other points, with a single point I describe the entire motion. Now with solids that's not the case, because every point in a solid that is rotating with a different circle. So this point is describing a different circle than this one, right? They are the same with respect to the same axis, but the radius is going to be different of that circle, right? So that's the case for rotational motion. Now, then whenever I have rotational motion, in reality, if I'm just interested about the overall thing, I can describe everything with a single point and say this is moving, which is what we have been assuming so far. But if the structures become a little bit more complex in shape and I want to pay more attention, then I need to analyze exactly how each point of that thing is moving. However, there is a good idea, a good mathematical concept, which is kind of going back to the point of particle, which is we can calculate what is called the center of mass of that object and then analyze just simply everything with respect to that center of mass. And center of mass of the object is, so to speak, to say what is the object where all the mass could be applied, and then we will be able to describe the motion. So in the case of the pencil and the thing, we're going to find that the entire pencil can be described as by following what's happening, let's say, in this point, and that point is what we call the center of mass, right? Or CM if you wish, or whatever you want to call it. Now the center of mass is going to have all the forces, so they're going to say it has the weight force. I could just see that point, and it's going to have the weight force of the pencil, and it's going to have the normal force of the table. And so there's no net force in there, and everything is good. But what happens when I keep pushing the pencil out of the table, and at some point the center of mass now, right, falls out of the table. Now we have a balance, we have an unbalanced force. This is the idea of center of mass. Now I'm going to have weight force of the point, but there's no normal because the center of mass doesn't have any normal, doesn't have any contact with the surface. At that point I'm going to have a net force, and it's going to be a force acting parallel. And this edge is going to act as like a fulcrum, right? Like an axis of rotation. And so what I'm going to find is that I have the pencil, and I can describe this as simply an object that it is receiving a force. Let's draw this again. I'm going to describe the pencil as a point where I'm applying a force, which is the weight, a distance from an axis, which will be the table, the edge of the table. And so what is going to happen when I am applying a force at the distance? That's what we actually define as torque, right? And what's going to be, that's a parallel force, is going to generate a rotation, and that's why the pen rotates. So what we need to find is exactly that center of mass and observe how that center of mass works, because the center of mass is also going to determine the stability. So how do we find that? Is the stability, it has a very simple rule, so we can describe it right now. Stability in here, right? And this is the things we're going to be analyzing is, take the object, and as extended as it is, find its center of mass. Let's say the center of mass is here. And then analyze the forces for that center of mass. The moment that the center of mass gets out of the table, let's say here, that's the moment that the object is going to fall. It will not fall, or it will not rotate in this case because it's extended. It will not rotate if the thing falls into the ground. Let's take a bottle of wine or something like that and say, okay, let's take a bottle of wine. And let's say this is the bottle of wine, maybe, okay, something like that. Where is the center of mass? Let's say the center of mass is here and the bottle is on the table. And I say, now I'm going to tilt the object. So I'm going to put it this way. And I'm saying, is this enough, or is this going to rotate or not? What do I have to do? I need to find the center of mass. If the center of mass, I take it down to the ground and it is in contact, the object is it's going to be fine. But if the object goes beyond that point, if the center of mass now goes beyond that, this object is going to drop. So that's the idea. Well, this is obviously a terrible drawing, but you get the idea. So you have to find the center of mass, make a normal, make a perpendicular line to the ground, and see is that ground covered or not by the surface. So the more the surface has, the more stable it's going to become, right? But if it's not stable at all, then if it's out of the line, then it's going to trip over because it's going to appear a torque, and that torque is going to make it rotate with respect to the axis, which is going to be the point of contact. Okay. How do we determine, however, that center of mass? And that's obviously a problem which you need, well, obviously, that's a problem that because masses have a standard and arbitrary shape, it's a problem that requires calculus, and we don't use calculus in physics 2053. So all that we're going to be analyzing is masses distributed in a discrete manner. So the same way that we were discussing for angular momentum in the case of inertia, we just said, okay, you will give in inertia unless it's m times r squared. It's kind of the same idea. Now the center of mass, we're going to define it, the center of mass, we're going to define that as x center of mass is going to be the sum. Let's say that we have a bar with no, the bar is massless, right? And this is made out of several different masses with mass 1, mass 2, mass 3, and they're at different distances. Let's say we could call this x. We could call, let's say, with respect to an axis. By the way, the axis you can choose whichever way you like. You will see that. We will see that in problems. But we can say this is at position x1, mass 2 is at the position x2, and mass 3 is at the position x3. So then, if you do the multiplication of the distance to the coordinate origin times the mass divided by the sum of all the masses, that's actually what's giving you the center of mass. And that's the only formula that we need. It will be provided anyway as all the other formulas. But the idea here is just to calculate the center of mass, the position of the center of mass. We're going to be using this formula. Now, of course, why the bottle is going to behave differently whether it's filled or not. And that's a problem, for instance, for containers in a boat, and we will see that when we see buoyancy and all those things. But if you don't distribute the containers in the boat properly, and there's a storm or whatever, and the containers move, or an airplane taking off, the load just moves, that's a recipe for catastrophe, because then you lose the center of mass. The entire airplane is designed to be moving with this distribution of forces, this and that, new stresses, new this and that are going to appear, and again, catastrophe. So, for instance, if I say this is 1,000,000 kilograms, and this is very light, the center of mass is going to be closer to the bigger mass. And we can see that from the formula anyways. We're going to make some examples in the problems. But the idea here is just to say distribution of mass is going to be, the center of mass is going to be proportional to the heavier mass is going to have more weight in terms of averaging what is the position. That's basically how you can calculate it here. This is an average position where everything is weighted with respect to the mass. I mean, that's if you've seen some statistics course, otherwise it might not make sense. But anyway, that's the idea here. The more massive the object is, the closer the center of mass is going to be to it, okay? And that's just captured through this formula. So 3 ideas in here. You need to have equilibrium, means there is no net force and there's no net torque. Second idea, center of mass. Center of mass captures the entire idea of the object. A solid extended object can be described just simply by a point. Analyze the equilibrium for that point, which is the center of mass, using this equation. Third one, if the center of mass drop down to the edge is not in contact with the surface, the object is doesn't have a stability, the object is going to fall. And these 3 ideas are all the ideas we're going to see in statics, because otherwise, again, it becomes very difficult in terms of the physics. So with this, we complete the description for solids. We can go to some problems. We started seeing what are the different states of matter, what describes a solid, and then we see there's 2 types of deformations that we apply in solids. We can apply deformations that compresses and stretch them, and those we call normal stress with a normal strain, proportionality given by Young's modulus, which is proper to the material. And we can also deform the shape, and when we deform the shape, we apply forces that are parallel to the area where we are applying that force. That produces a shear stress, that produces the result or arises as a result of a shear strain, which is how much we are distorting from the original position divided by the distance, and the proportionality or the elasticity is given by the shear modulus. And once we have defined the deformation, we also can introduce the idea of equilibrium and statistics. Statistics is describing why objects do not move. To describe solid extended objects, first calculate the center of mass and see for that center of mass whether there is no net force, whether there is no net torque. And once you've observed that, and you can also use the criterion of stability, write the center mass, bring it to the ground, see if it's stable or not. If it's stable, wonderful. If it doesn't fall in there, then it's going to fall over. Okay, so these are the concepts. Now let's see some problems, because many of these ideas are going to become trivial when we apply them. So problem number 4 in discussion says there's a piano wire that has 1.6 meters long. So we can define that the unstretched direction is 1.6 meters long and has a diameter. So if we observe the string, the diameter, which is twice the radius, it's equal to 0.2 centimeters. That means that the radius, of course, is going to be 0.1 centimeters, which is the same as 0.1 10 to the minus 3 meters. Once we know the radius, we can calculate the area of the wire. The area of the wire is going to be pi r squared. So it's going to be pi times 0.1 squared, which is going to be 0.1 10 to the minus 3 squared. And that's going to be 10 to the minus 1. Correct. So that's going to be 1 10 to the minus 4. So if we do that, that becomes much easier, because then we can write pi times 10 to the minus 4 squared, that's 10 to the minus 8, so it's pi times 10 to the minus 8 meters squared. Okay, that's with respect to the area of the wire, and then they told us that the Young modulus of steel, I think it's 210 to the 9 newtons per square meter. Very important here to work in international units as much as possible to avoid errors. And again, become acquainted with the scientific notation. If you're not, it's a prerequisite for Physics 2053. It takes 5 minutes to see it. Calculators also operate with that. If you prefer to write numbers, good luck, because you're going to be adding 9 zeros here, you're going to add 8 zeros here, you can add 4, it's just a mess. So don't do that. Okay, so the question is, how great is the tension if the wire is stretched 0.25 centimeters when tightened, right? So they're telling us that we're stretching 0.25 centimeters. And again, first thing we do, we just go 0.25 is 0.25 10 to the minus 2 meters, or we can rewrite 25 10 to the minus 4 meters. Okay, that's the deformation that we are applying. So from here, the first thing that we can calculate is the strain, and the strain is defined as the change in length over the original length. The change in length is 25, 10 to the minus 4, and that needs to be divided by 1 times 6. And that's going to be 1.56 10 to the minus 3. And what are the units of strain? Unitless, it's dimensionless, excuse me, because there's no dimension. This is length divided by length, so there's no dimension. So that's the answer for that. And now the question, of course, is what's the tension, right? How great is the tension? Let's remember this is a string, and so we're going to be applying a tension here. That is the force of tension that's responsible for the deformation that in its own produces stress. So the stress is Young modulus times strain deformation. How much is Young modulus? 210 to the minus 9, excuse me, 10 to the 9 times 156. You also can write this as 210 to the 11, okay? The 2 zeros going in there, but it's okay. And then epsilon n is 156 10 to the minus 3. If we do that, then this is 10 to the 11. Becomes much more obvious, because once you put 10 to the 11, 11 and minus 3 is going to be 10 to the 8, and this is just simply twice this, which is 3. Let's say 3. 3.1, but it's okay, 3.12, something like that, but 10, 8 sigma, and this is going to be newtons per square meter. And because we're working in an international system, there's no confusion, this is very easy. And what is the definition of a stress? A stress is just the force divided by the area. So now if we want to know the force, that force is a tension force, because we're stretching, and then this tension force is going to be the normal stress times the area of the wire. And so the area of the wire we calculated over here, the tension of the stress we calculated over there, it's going to be 3.1 10 to the 8 times pi, which is also 3.1, let's say as a first approximation, 10 to the minus 8. So it's like 3.1 squared, which is going to be 9, about 9. Okay? So actually there's an error in here, I just realized. Radius 0.1 centimeters is not 0.1 10 to the minus 3, but 10 to the minus 2. Now this is 10 to the minus 3. And when you go back here, it's going to be 10 to the minus 3 squared. So that's going to be 10 to the minus 6. So instead of being 9, which in fact was 9.8, when we go to the area, all of this remains the same. That is correct, that is correct. And when we go to here, that's correct. But when we go here, we have to multiply times the wire area. And the wire area is going to be 3.1. We're allowed to do that, but that's going to be minus 6. So when we multiply this times this, 3.1 times 3.1 is about 9.8. And 10 to the 8, 10 to the minus, 10 to plus 2, right? 8 minus 6, 2. So that's actually equal to 980 newtons. And that is the force that we are experiencing, or that we, are applying to produce that deformation. Now, question B, is this going to be breaking the string or not? And the question here says, the question says if the maximum tensile stress and compressive stress, so the maximum stress, the maximum, and they say this is tensile or compressive, so there's no difference, but also we know that it's going to be normal, and that's equal to 0.5 gigapascals. Is this going to break or not? So how do we figure out that one? Well, 0.5 gigapascals, pascals is Newton per square meter, giga is 10 to the 1, so 10 to the 9. So 1 giga is 10 to the 9, right? So 1 gigapascal is 0.5, 10 to the 9 pascals. The pascals are newtons per square meter, so that we have the same units anyways. So that's going to be 0.5, 10 to the 9 newtons per square meter. How much is the force, the maximum force that we can apply to produce this maximum stress? After this stress, the thing is done. So how much force we can apply? Well, this stress with this area is the same thing we just did over here. So the maximum tension that we can apply is going to be the maximum stress times the area. The maximum stress, 0.5, 10 to the 9. The area of this is pi 10 to the minus 6. Well, that's going to be 3 that's going to be 1.5 about that. And 10 to the 9, that's going to be 10 to the 3. So what is the maximum tension? 1500 newtons. So we're about 2/3 into the 1500 newtons. That means that we are safe to use this. However, how much safe you are, it's actually a matter of design. Engineers never say, oh, the maximum stress is 1500 newtons, so we can apply 1400 newtons. Nobody would put its life into that sort of calculation because there's many simplifications and many things that can go wrong. So usually engineers use what they call a safety factor, which might be, if this is the maximum tensile stress, maybe let's assume instead of this is half of it, or it's a 10th, or it's a 4th, or it's a 5th, or something. So in case we made some errors, we are still far away from the dangerous area, okay? But that's a matter of prudence, not more than anything else. But in this case, if the answer was 1500 and the answer is about 1000, then yes, we are safe, or there's nothing safe because it's a piano, but basically the piano string is going to hold it. Okay, so here again we see how we deform solids because we produce a deformation. Because we produce a deformation, then this needs to erase the stress. The stress eventually is just the result of the force, in this case tensile. And let's see if the maximum tensile force that we can apply is 1500 and we're having here 1000, we're all safe. Let's see more examples. So problem number 5 is an example of shear. It's the one where we are going to produce a deformation that doesn't change the size, it changes the shape. So we're saying there's a box-shaped piece of gelatin dessert that has a top area of 15, let's write that thing, so like this, and this is jelly and it's on a plate or something, right? And so we're applying a force at some point, right? But the area here, it's 15 square centimeters. And immediately we know that that's 15, 10 to the minus 4, square meters. And the height of this piece of gelatin, what we call h, is 3 centimeters, which immediately, of course, is 3 10 to the minus 2 meters. When a shearing force of 0.5 newtons is applied, so when the shearing force is 0.5 newtons, so we have the block, and so we're applying a force in here, and that force is 0.5 newtons. The surface displaces 4 millimeters relative to the bottom surface. So basically what we have is, initially we have, let's make a cross section, we have this, we apply a force, and so we end up having this. And how much is this displacement? Well, according to the problem, that is 4 millimeters. And we want to know the stir, which of course is 4 10 to the minus 3 meters. So always try to convert into international units. It says what are the shearing stress, the shearing strain, and the shear modulus for the gelatin. Okay, so we're going to have to find everything. So let's start with the stress. Stress, shear, is defined as the force parallel divided by the area. What is the force parallel? The force parallel is 0.5 newtons. What is the area parallel? No, the area. 1.5 10 to the minus 4. So that's going to be 1/3 10 to the 4 newtons per square meter. Okay, what else? What is the strain? Well, the strain in this case is given by the change in position with respect to the height. The change in position is 4 10 to the minus 3. The height is 3 10 to the minus 2. So how much is that? That's 4/3 10 to the minus 1, and this is dimensionless. Okay? And the final question is, how much is the shear modulus? Well, that's given by the equation. Shear is shear modulus times epsilon shear. So that means that's going to be 1/3 10 to the minus 4 to the plus 4, excuse me, divided by 4/3 10 to the minus 1. And how much is that? That's actually 1/4 10 to the 5, or equivalently 0.25 10 to the 5, which is 25 10 to the 3 newtons per square meter. So with that, we complete everything. So actually, this is how you would measure the shear modulus of something. Is apply a force that you know over an area that you have calculated and determine the stress, then also characterize how it deforms, and from those you actually derive this. And then you would go to your handbook and write down, for this gelatin, this is the shear modulus, 25 10 to 3, so 25 kilonewtons per square meter. So problem number 7 says there is a bar. The bar has it's 100 newtons bar, so that's the weight of the bar is 100 newtons. It's another way of saying that the bar is about 10 kilograms. And it's resting on a fulcrum, and in one end of the bar we have a weight which is 500 newtons, excuse me, and at the other one we have another force that is 200. So if I ask you, if I'm pulling from two sides, and remember we said which one, how is easier to rotate this pencil, if I push like this from the middle or if I push like this from there? So it's much easier there. So then the higher the distance, the more torque. So where am I going to be placing the fulcrum is probably closer to the higher force, because this is multiplicative with the distance. So I want to reduce this. I reduce it by bringing it closer, which at the same time is increasing distance in here. So it's multiplying this. So it's actually in equilibrium, because the question is, where do we place this? So this is in equilibrium. You can try yourself, push down stronger and lighter here. You can actually achieve that whenever you're bringing the axis close in there. So the question again is, how do you place what excuse me, what are the distance of the fulcrum? A very important thing here to realize is that the origin of coordinates that we can take, it's irrelevant. We can take anything to be 0, which in this case we're probably going to take this to be the 0 point. And why is that irrelevant? Because if the balance of forces is 0 here, it's going to be 0 also in any other one. Why? If it were not 0, if I choose another axis, in this axis is 0 and this one is not 0, that thing it will start rotating in this one. But an object that is not rotating with respect to no axis. I mean, there's no axis with respect to which is rotating. So you cannot say it's not rotating with respect to this axis, but it's not with the other one. It's not rotating. So if the bar is in equilibrium, it's not rotating in any axis. So I'm free to choose whichever axis I want to choose, right? If it's in equilibrium, again, this is the important thing, if it's in equilibrium. So then I can choose this as to be the 0, and then I can define the distances accordingly. I know that the bar is going to be the length of, the bar is going to be a length of L, let's say, well, we're not given the distance anyways. And the question is, what is the reaction force exerted by the support on the pipe? Okay, So there are many different ways in which we're going to be doing these things, but there's two conditions always for equilibrium. The first condition is that the forces need to be balanced. So let's make first force equilibrium, okay? That the sum of all the forces, it's equal to 0. So we call this one in the theoretical introduction. So how do we achieve that? Okay, let's make a free body diagram, and let's say that there is a weight of the bar, there is a weight of the 500 kilograms, and there's the weight of the 200 newtons. What forces is going up? Well, that's the reaction force of the fulcrum, right? That's a normal force of the pin of that. And so I need to make sure that the force of normal, it's minus the 500 newtons, minus the 200 newtons, minus the 100 newtons. That's equal to mass times acceleration in y. But this is an equilibrium, it's not moving, that means to be 0. That means that the normal force is 700, 800 newtons. Now, of course, the question is, with this reaction force, which is the fulcrum is going to be in equilibrium always with respect to vertical motion, always, because it's going to compensate. It doesn't matter where you move it. There is no distance in here, right? This is the bar. The bar is experiencing the same forces regardless of where I place this. But the second condition, which is the condition of equilibrium for torque, is not going to be independent. Why? Because I have a force that is applying here at the distance there. I'm going to measure the bar, and I'm saying, here's the fulcrum, and I'm saying I'm applying a force here which is 500 newtons. So I'm applying a force at the distance, and I'm going to call that x. So what I have is a force at the distance x. I have a torque of 500 times x. And on the other hand, I'm going to have another force, which is a force of 200 newtons, and it's acting 200 newtons at the distance. If the bar, let's say, has a length L, this distance is going to be L minus x. So it's acting on a distance L minus x. And that's a very important thing. The weight here is trying to make this rotate clockwise. Okay, if I have a bar and I pull down, this rotates clockwise. If I have a bar and I pull here, it rotates counterclockwise. So the torque here should have the negative sign. So we're choosing that to be the positive direction. Okay, so the torque, which is positive, to be clockwise. So choose whichever criteria you want, positive or negative, but you have to stick to that. Okay, and then finally is what is the contribution of the torque as a result of the weight. And to find that, of course, we just place the bar and assume it's homogeneous. So that's going to be the weight. And the weight also is going to be a distance from the fulcrum. Now remember that the center of mass is defined as the point where we can analyze all the forces acting. And so the weight, we can apply it on the center of mass. But the question is, where is the center of mass? So we don't know that. Well, we actually know. Because the object is homogeneous, the center of mass is going to be half on the object. So from here to here, we have half of the length. Now, of course, the question is, we can just rewrite the thing. So we have the fulcrum, we have the 500, we call this x, we call this L minus x, because the entire thing is x. Here is the 200, and here we have the 100. And the question is, what is this distance? Okay, well, this is not at scale, obviously. Let me bring it a little bit closer. But this weight is going to be halfway through both. So from here to here is L half, from here to there is going to be also L half. So that means that the distance in here is L minus x minus L half, and that's going to be L half minus x. So the distance from the weight to the fulcrum, which is the axis of rotation, it's L half x. And then I can just do finally that the sum of all the torques need to be 0. And again, careful with the signs. If I pull here, where is this thing going to rotate? It's going to rotate towards there. So according to my sign, that should be negative. Okay, so that's going to produce a torque which is going to be 100 newtons times half L minus x, but with a minus. I've chosen to put that thing there. I could have chosen to put it somewhere else. We're going to figure it out anyways, right? Because x could be here, could be there, so we're going to figure it out. We're just taking this to be the origin of coordinates. So if one of the distances ends up being negative, then we know that the origin of coordinates is like towards there, right? So, so let's write all these balances. So we have, on the positive, we're going to have 500 times x. So we have the 500 times x. minus the one for this one, which is negative 200 L minus X, minus 100, that's the weight torque, L half minus X. And that needs to be equal to 0 because this is in equilibrium. So we're going to have 500 X minus 200 L minus 200 X minus 100 L halves, which is the same as 50 L, plus, oh, and this is plus, this is minus minus plus, plus 100 X, and that's 0. So let's add up. That's 500, 700, 800. So we have 800X and what else? Minus 250L. And that needs to be 0, which means that X is going to be 250 divided by 800L. And that is going to be, so in terms of 50, that's 5, and this is 16. So that's 5/16 L, that's 0.31 L. So let's make sense of this. The sign is correct, the sign is correct. Okay, so we said, where do we place the fulcrum? The fulcrum needs to be, if we take to be this the 0 point, yeah, we take this to be the 0 point, but we can just everything shift, right? So whatever you put the fulcrum and then you move the bar, such that this weight is 31. So if the bar is 1 meter, this should be 31 centimeters and 69 centimeters towards the left. That's basically the answer. So we found where is the bar. So because this is arbitrary, depends on how you define the model. So if you put here the 0 or the coordinate system, you're going to have the 200 newtons at 0. Half of the 1 meter is going to be at 500, we're going to have the weight. And how much you're going to have? Where is going to be the fulcrum? The fulcrum is going to be like half a meter, here. Half a meter minus X. How much was X is 31. So you're going to have 500 minus, or 0.5 minus 0.31, which is 0.19, right? So and then 19 centimeters from the middle point to the fulcrum, right? Anyway, you can play with these numbers if you want, but basically at the end of everything, you're gonna, if you call this X, that's going to be at 0.31 L. Basically, we can determine with this how we move the bars with the weights such that this thing gets in equilibrium. So how do we achieve that? Of course, we have to attend to the forces that are acting, but do not forget the weight force that is acting in here, okay? And that's a very, excuse me, that's a very important thing. The reaction force of the fulcrum is going to tell you whether this thing is going to hold it or not. If it is not strong enough, it's going to break, so it will not hold it. But this is just equilibrium for translational motion. So this collapses, it just drops to the ground, right? Or to the floor if there's the floor in here. But the torque analysis is going to tell you whether the thing is rotating or not. And that's the second condition of equilibrium. So the first one is just telling you it doesn't move, we forced it. So if this is 800 newtons, does it rotate? It does not. If we place this such that all those forces acting tangential and at a distance that is producing torques are in balance, such that this thing is in equilibrium. Let's see another example. So problem number 9 says that there is a beam suspended on its two edges. And on top of that, there is a beam of half its length. So let's try to make something closer, probably. So it should be about half of that. This beam over here has a mass of 940 kilograms. So the other beam, which we could call B, mass of B, it's half of that, because that's going to be 470 kilograms, right? And they're asking us, because it's half, it's identical, but just half the size, so half the volume, half the mass, still has the same density, half the volume, you have the mass. So a uniform still has a mass of 940 kilograms. On its resting, half of an identical beam. What is the vertical support force at each end? So we're going to find the force here and here. How do we do that? Always we do force balance, okay? Diagram, free body diagram. So let's go for the first part, which is going to be that the sum of all the forces needs to be 0. Let's see the forces of each one of these things. So we have, if we make a free body diagram, we take the entire structure to be, we're going to have the following. Force pulling down is the force of due to weight to 1, or A. Another force that pushes down is the force of B. So we have the force weight of B. What else do we have? Well, we also have force A. Let's say we call let's call this L, and this we call R, left and right. So we're going to have the reaction force of length, because this pushes down, this pushes up, and we have the reaction force R. And so we see that the force L plus force R minus force weight B minus force weight A, that's equal to mass times acceleration in Y, but this is 0. That means that the force on left plus the reaction force due to the R needs to be equal to the weight of A plus the weight of B. How much is that? That's going to be, so let's say 1,000, 1,500, so 1,410. So that's going to be about these newtons. Okay, because it's about 1,500 minus 60, 90. Correct. So that's going to be it. 1,400 and 4,010, that's going to be 1,410 is you add them together times G, that's going to be that, right? The weight is mg. Okay, very good. So that's going to be the forces. That's with respect to the first condition, which is the condition of not moving up and down. But we have two incognitas in a single equation. We need another one. Where are we taking the other one from? From the torque. And here comes the beauty of torque. Equilibrium. First, we choose what we want to call positive and negative. Before we chose going clockwise positive, now let's choose going counterclockwise. It's what we call positive now. We can choose this. It's free. It's a free country. Okay? And the second thing we have to choose the origin for, on which we're going to calculate all the forces. And in this particular case, that we can choose whatever. It makes sense to use one of the fulcrums, so we get rid of one of the equations. Why? It's because once you align the axis upon which you are analyzing rotation to be aligned with one of the forces, that thing goes out of the equation, because that's that force times the distance, but the distance is 0 because it's in itself. So it doesn't have a torque, right? Any force that acts on the axis of rotation doesn't really add in rotation. You have to be applying a force at distance, right? The torque is force tangential times distance. If this distance is 0, torque is 0. So if I align the axis with one of the fulcrums, then I get rid of that. So let's say we align the torque in here, excuse me, the axis in there. So in the position of L, right? So then we're going to have the following. Let's make the bar, and let's make the second bar. And we realize, what are the forces? First of all, there's the weight of one bar is acting at half the distance, because that's where the center of mass is. It's an identical homogeneous bar. The center of mass is going to be calculated at the center of that thing. But we also have another force, which is the force due to the force of B, and that's also going to be acting at the center of the beam, but now that's a quarter, because it's half the bar, so it's a quarter of the length. Okay, and finally we have on point R, we're going to have what? We're going to have force reacting here, which is F sub R. Okay, so let's analyze this. Let's write the entire thing saying I have a single, very good, this is the axis, and so I'm going to have one force here, which is 460, so 4,700 going down at a quarter of the length. I have another force here at half of the length with 9,480 newtons. And finally, I have a force at the entire distance, capital L, which is going to be the reaction force of R. Not R because reaction is R because we say left and right, okay? That's the normal force of R on there, okay? Very good, so let's do the torques. What torques do we have? We're going to have torques positive are the ones going up. So which ones with respect to the axis? This is going up, so that's going to be what? That's going to be the force of R times the distance, which is L, plus any other positive ones? No. What about these ones? These ones are going to try to make it rotate clockwise. We have to find counterclockwise to be positive in this case. Now clockwise is negative. So 9,480 times half. That's that torque. Minus 4,700 L fourths That's the torque of this force. And any other forces, you could say, yeah, well, there's another torque which is in here. Let's add one. That one is positive, right? Because that is a force reaction of L, we said, the force reaction of left. But what's the torque that that one does? Well, that's going to be the torque of L is going to be the force of L times the distance with respect to the axis. 0. There's no torque on that, so we don't really. That's why it's so beautiful to put the axis in here. We could have done it here, and then the torque due to this is 0. If we put it in the middle, then we have two torques to calculate. But anyways, you can put it anywhere that you like. Everything is going to be relative to that axis. And because the thing is not rotating, it's not rotating with respect to none of the axes parallel. Okay, so you can freely choose whichever you like, and you can also choose this sign whichever way you want. Because at the end of everything, at the end of the day, the entire torque, the net torque is 0. So I can do a minus here, minus 0 is 0 anyways. So it is still holds, right? Very good. So we have all of those things, all of those freedoms, let's say. We can say that this is equal, of course, to 0 because this is in equilibrium. So what that means is that F sub r times length is going to be equal to 14,100. There's a 0 missing here. So 14,000. Does that make sense? 4,000. It's going to be 13. 1410, yeah, 1410. So where did I make a mistake? There's no 800 in here, that's a 0. So that's 9,400. Okay, that's 14,100. Oh, no. Sorry. This divided by 2, that's minus 4,700 L. This divided by 4, that's 1,100 and probably 75 L, and that's equal to 0. Okay, now we can add these two together, and that's going to be 5,875 L. This is L, and this is F sub r, and that needs to be equal to 0. And so I can cancel N and L all over the place. And so I'm going to have that F sub r, it's 5,875 newtons. So now I found what is the reaction force in here, not through the forces acting on them, but from the fact that it is not rotating. This is what is so wonderful. I mean, obviously, when you're an architect, you define a structure like this, you don't want to think, if this was the roof, you wouldn't want the roof just, because it would be, or the floor, right? If the floor goes like that, everyone, So that's the idea. Anyway, 5,875 newtons are acting on here. So how much is the force on here? Well, because that plus the force in R is 14,100, the force in left is going to be 14,100, or yeah, basically 14,100 minus F sub R, which is that thing that we obtain up there, which is going to be 25 in here. That goes to 900, that's a 2, and that goes to 6, which is 8,225 newtons. That sounds about right. So 8,225 newtons is the force in here. 5,875 is the force in there. We can solve this selecting the axis in here, and you're going to do the same. Now, if you select the axis in here with the current convention, then these torques become positive, but this one is going to be negative. So you would have this minus this, and this is going to be times L. Okay, if you choose the axis in the middle, you can have this and this, but you don't have torque from here, but you have the torque from there. This will be positive in our convention, this will be positive, but this will be negative. So depending on how you choose, you're going to have a different frequency, but it doesn't matter because it's in equilibrium. And because it's in equilibrium, it's not rotating. It is not rotating with respect to non-axis, so we can choose the coordinate axis wherever we want. Try this yourself. Try it with maybe the solution here, maybe the axis in origin in here. Of course, once you change the origin, you're also going to have to change the distance, right? The distance with respect to the axis upon which you were calculating the rotation. But because now I decided, what is the rotation with respect to this axis? There's none. So that's why the torque is 0. But the distance are going to be always with respect to that, because the torques are with respect to that. So that's basically the idea. There's nothing more in here in terms of these elements. The idea here is, of course, remember, center of mass is going to be in the geometrical center of the figure. If the figure is a beam, it's going to be in the center. If it's a sphere, it's going to be in the center. Whenever the shape is much more complicated, we cannot do that in physics 2053. The only exception is if, for instance, we have two masses in a bar, and we say we have two masses at a certain distance. But usually we're not going to mix problems because this is enough, right, in terms of complexity, which is not really complex, but it's just the idea is because we understand the fact that things are not moving vertically, they have net zero force. And so from that we can find the balance of forces, but also because things are not rotating, then the torque is zero. And because torque is zero, then we can use that also to find the supporting forces. And if we were designing something like, for instance, let's say, oh, this is a pillar that goes down to the, let's say that this was the roof or whatever, right? And say, oh, can I put, for instance, a swimming pool in here, that this will be like the swimming pool, and I put a load, and my load is applying in that area, only in that area, not the other one. Is this floor going to collapse? Is it going or not? So I'm going to find the equilibrium things. I may even find like, oh, how do I find the equilibrium? And then I find how much is the weight or the load on this column, and then I can see, is this column going to have enough strength to hold that or not, and all those things. Or we can even calculate the, this becomes more difficult, what is the stress across this beam, which will be the floor if I put a swimming pool, right? So it's because swimming pool has a lot of water, and that's actually a lot of weight, so it's a lot of load. But all those things are things that the structural engineers are going to be calculating, and with very simple math you can introduce yourself, so next time that you walk around you can start seeing, oh, loads here, then there's stress here and there, and all those things, right? Maybe. So anyway, that's basically the idea for this. As a torque, let's just see one problem for stability and understand the concept applied in a particular scenario. So let's discuss the last topic of this chapter, which is the chapter of stability. Now, obviously, when we have an object standing on a table, let's say this is the object and standing on the table, we say, oh, this object is stable. Why? Because it's not moving, and if we just try to push it a little bit, it's not going to move. But the idea here we're asking is how stable it is in terms of torques, because what we're considering is, will this just trip and go over, right? So if I take this object and I lift it, let's say from a corner, right, and I just lift it like this, let's say, my question is, okay, well, let's do it a little bit, just a little bit, right? What happens when I release it? Well, if you release it, it's going to go back. So in this case, it's going to be not going to go all over. So how much do I have to push to actually make it go back? So you would have to do it, to lift it like a lot, right? Like this. So you would have to go from here and push it, so when you release it here, it actually will tip over there instead of going the other direction. Of course, the rotation is going to be a result of a torque, because once we stop pushing, then we're going to have breaking the balance. When I'm pushing, this is an equilibrium, zero torque. Once I release that, forces get out of balance, and net torque appears. The torque is going to make this thing to rotate, okay? And the question is, which one is going to be the direction? That is given by the criteria of stability. And it says, find the center of mass of an object, and see, if I take the center of mass, this is the center of mass, and I project it directly vertically down, if that thing falls within the base, this is the base, then it will go back to that position. So in which case am I going to be going over? Well, as I increase the size, let's make an intermediate step. As I increase the height, if you observe what's happening, in here the center of mass falls over here in the base. In here the center of mass falls over there. In here the center of mass falls over there. If I increasing it, in here the center of mass falls just kind of in the corner. The moment I go farther, the center of mass, when I go down, doesn't fall anymore through this layer, it falls in this one. So now the new equilibrium is going to be to fall in that one. So that's going to be equivalent as if I had this object and I was pushing that way to turn it that way. So here of stability is then take the center of mass, make a line all the way down. If it falls within the base, then it's in equilibrium. If not, it will not. Of course, it's in equilibrium when I'm holding the force. Whenever I release it, it will go back to equilibrium, right? And equilibrium being on the ground. So whether something is stable or not, it's going to depend on whether that center of mass is falling once I drop it vertical, if it's falling through the base of support of the object. So the question now is question number 10 in the discussion. It says the Leaning Tower of Pisa, which is 50 meters tall. Let's assume it's a block, okay? It's a 55 meters tall, and has a base of 7.7 meters in radius. Well, the radius of the base is 7.7 meters. That's telling us that actually the entire base is going to be twice the radius, the diameter, so it's going to be 14 or 15.4 meters is the diameter, right, of that base. And so it's telling us the top is 4.5 meters off center. So we can write the tower. This, of course, is not going to be up to scale. but this distance is 4.5 meters. Now, because it has the form, we could say there's a shear, right? That's a stress. Is the tower stable is the tower in a stable equilibrium? If so, how much farther can it lean before it becomes unstable? Assume the tower is of uniform composition. So the fact that it's in uniform composition is essential, but we're going to be assuming always that because we otherwise need differential calculus and we cannot. And of course, the center of mass is going to be in the middle of the tower. So the tower is 55 meters. That means that in 27.5 meters, we're going to find the tower. Okay. We assume also that the leaning tower of Pisa is 55 meters straight, so it's 55 meters in this direction anyways, okay? And so the question is, will this be in equilibrium or not? We have to take the center of mass, bring it down, and see, does it fall within the basis or not, okay? So does it fall within the basis or not? And so in that case, right, so we're going to go from the stable position, and it falls within the base. And in fact, it's supported, so this doesn't even move. But once I displace it, now I need to take the base and see, does it fall within the base? Because if it doesn't fall with the base, if it falls, let's say, more obvious, not anymore within the base, but within this other layer, when I drop it, it's going to fall in that one, right? Okay, so if I let this object go, it just falls there. If I let the object fall when it's, let's say, like slightly, where this is obviously within the base, it's going to drop that way, right? So the torque is going to go this way. The torque in this case is going to go that way, right? So that's what we're discussing, as we just said before. Okay, so the question is it in here equilibrium or not? So to see that, we have to see where this center of mass falls with respect to the basis. And of course, because it's 4.5 meters, the thing that we can realize is that this is going to be with respect to the, let's make the diagram. Okay, and so let's make it less. Better. Okay, and so now we have the center of mass. What is the center of mass in the tower? It's just 25 or 27, right? The distance half here. And how much is the distance vertical? That's 7.7 meters. So because this object, but how far is this from the original position? 4.5 meters. So once I bring it down here, how far is going to be from its original position, the center of mass? How far is the corner with respect to the center, with respect to the original position? It's in the same position, okay? But how much is that one? Well, that one is going to be 4.5. So what about the center of mass? The center of mass is half of the height, therefore it's going to be at half of the height, it's going to be at half of the distance. From 4.5 to 0, 4.5 to 0, from 0 to 55, so 27.5, which is half, 2.25 meters in there. So the distance in here is 2.25 meters. But because the base is 7.7 meters, or 55 per 4, let's assume this is, that means that if I take the, let's say, the center of mass being here, once I tilt it, and again this is sort of exaggerated anyways, the new center of mass is here. This distance from the previous to the other one is 2.25 meters. But because the center of mass I have as a distance 7.7 meters, this object is, yes, within that, within equilibrium. So how much can we pull it? Well, we could pull it all the way so that this ends up being at 7.7 meters, because that's the maximum we're going to be able to go, right? If we keep tilting, so the center of mass displaces as the same as the base. So the maximum that we can displace at the center of mass is going to be 7.7 meters. But 7.7 meters, how much is at the top? Well, it's twice, 2.25, 4.5. So we're going to go from 7.7 to 15.4 meters. But we have displaced already 14.5 meters. So how much more can we at the top is 7.5, because we already have 4.5, it's going to be 15.4 minus 4.5, and that's going to be 10.9 meters. So the Leaning Tower of Pisa might move 10.9 more meters and still be in equilibrium. The moment it goes farther than 10.9, then what's going to happen is that this thing is going to be completely aligned, completely out of here. So the center of mass will be there, let's say, so we have to build it, and at that point it's going to start dropping outside, so the equilibrium will be just to tip over, right? And if we see a boat, we will see like capsizing or whatever, right? But this is basically the idea. We need to see the line, bringing it down. Does it fall within the base of support? If it does, it's in equilibrium. If it doesn't, in a stable equilibrium, we mean. If it doesn't, then it's going to be tipping over, because it's going to be a net torque as soon as we remove whatever is holding the thing in position, right? So we can keep pushing, and at some point you tip over, and poof, that thing falls. Which is then what explains our experiment with the pencil with which we start the class. We have a pencil on the table and we keep pushing, and everything is fine. But as soon as the center of mass of this object falls outside of the support area, you're going to have a net torque, because that weight, right? If we take, let's make it here. We take the pencil and it's on the table and everything is fine, but as I advance more and more, if the pencil is in a scenario where the center of mass is in here, all object that is in here is weight, so I'm only going to have a weight, and I'm going to have a normal force, so there's not going to be net torque. But the moment I release that, I put that weight above the edge of the table, there's not any more normal acting in here on this point, which is all that matters. So actually I'm going to have fulcrum here, an axis there, and as soon as the center of mass goes through the axis, now I have a weight acting at a distance, therefore I'm going to have a torque. Excuse me. The farther away you go, the higher the torque, and of course torque is inertia times alpha, so the higher the angular acceleration. So if I take the pencil or the marker, here is stable, and one point, at some point, I keep pushing it, and at some point, the center of mass is not going to be enough to recover and it falls. But how much farther away? Well, actually, because of the cap, I think. How much farther away? So if I drop it from here, it goes like that. If I drop it from here, it's much faster, right? Because the distance, the distance increasing, the torque is higher, so the alpha is increasing. So, well, we will have to calculate also the moment of inertia, but that's going to be the mass times the radius. It depends on a particular distribution, excuse me, of the pen mass. But anyway, that is basically the idea. Now we can see the idea of stability in here as soon and based on the equilibrium conditions. Vertical for translational in this case, but also torque in terms of rotational motion. As I push the pen, the center of mass is all I care, because there's no single object. There's not like with the beam that we were applying forces. This only force here is the weight, and weight is sustained as long as it is on the base. But as soon as the weight overcomes the edge of the table, that weight is producing a net force without any counterbalancing force. It's producing a torque, and that torque is going to be responsible of rotating that thing, it tips over. That's the idea here of stability. Conceptually, we can apply it. Examples are going to be very simple. Whenever you have a problem of stability, make the diagram of the object, find the center of mass, which is going to be the geometrical center. Most of the cases we're assuming homogeneous masses. If not, maybe you have to think, and then see where does it fall. Does it fall within the base of support? All good. Does it fall outside? It will tip over and fall. Okay, that is the idea here. We can see it maybe with the pencil as well. So a little bit of pushing might be fine. A little bit of pushing might be fine, but if I push too much, at some point, the torque inverts, it just falls away. That's what happens because the base is very small. Whereas if I have an object that has a bigger base, like this one, if I push it, I can push it much more, up to it just falls, right? So the wider the base, I can tilt it more because more of the base is going to be falling within the base. As I go like this, more of this is going to fall. But at some point, if I do this, that doesn't fall anymore within the base, so it just tips over. The larger the base, the more stability you have. And the other thing is also the closer it is to the ground. Why? Because if I have a tower or like whatever object, right, and the center of mass, I have this one over here. Because of the distance, you have to think that this is the sine, because it's just tangent and all of those things, right? So let's say this like that. So depending on the angle I have in here, I'm going to have the angle in there, right? Which is going to be telling me, this is normal, so it's going to be telling me the center of mass where exactly it's going to be. And that eventually it's determining where the center of mass it is. So the farther away the center of mass it is, the longer the distance is covering. Think of that in terms of S as the arc is the radius times theta, right, the angular position. So this distance is going to be larger the farther away that you're from the radius of rotation. So if I have that object with respect to that axis of rotation, let's make this, and let's make this. The center of mass is here, the center of mass is in there. As I start to tilt, this is going to be the radius, and it's going to be kind of, if you wish, the distance. So that distance is higher, right? So that's going to be much more easier to get out with a displacement out of the base, whereas in this case it's not. So ways that you can increase stability, increase the base, but also bring the center of mass down. So for instance, if you are in a tall thing, maybe put more mass on the ground, right? So it's longer, but the center of mass is not geometrically in the center, you bring it down. So you increase stability by increasing the base, so you have a larger base of support, but also by bringing down the center of mass, such as when you tilted the center of mass in the vertical line to the floor, that's still fall through the bases, right? So the two ways through increase of mass down, bringing down the center of mass increases stability. That's why also it's easier to push a friend when it's like this, that if the friend squats, the mass is the same, but now you have redistributed. If you push it when it's like that, it's much more difficult, there's more mass. The center of mass is closer to the ground, so it's easier for him to remain in position. And equivalently, if someone has, it's easier to push a friend when he's standing on 1 foot. The base is smaller than when he's standing with 2 feet, or actually with 2 feet and well extended. Sort of the base of support is increased, right? So those are the concepts of stability that we can use to analyze situations in equilibrium. Mathematically, we're not going to be playing much. This is just a particular example, but mostly we're interested in qualitatively understanding why this thing falls or why it doesn't fall, and how we can, mathematically, then we can use equations of equilibrium. But that is pretty much it. So we see how solids deform, what is the ultimate reason to say microscopically, and also how solids have equilibrium whenever there is no net force, whenever there is no net torque, and if that thing is not fulfilled, that's because maybe the center of mass is displaced. So we understand stability. If the line falls through the, if it falls out, it's going to tip over.